All right. Yeah. Hi, everyone. My name is Jared. As he said, I am here to present on behalf of Hannah Sargeant. She put all these slides together. I am simply a co-author here involved, but for a lot of the questions, we may have to defer to Hannah, and I am happy to set up a discussion for any of that. So, without further ado, let's get started. This study is investigating dust cloud formation from moon rovers and how we can model these using discrete element models. Right on. It is. Oh. Okay, sorry about that delay. So, as we all know, the moon is covered in a fine layer of regolith that poses hazards to human health and equipment health, if you will. Dust mobilization methods include interactions with surface electric fields, meteorite impacts, and especially human activity. Here we see the Apollo 16 LRV traverse just making an absolute mess as they go flooring it around the lunar surface. So that's something we're probably going to want to try to avoid. Dust mitigation techniques. Kevin Cannon gave a very good review of this in a recent paper. Include limiting dust mobilization, preventing dust collection, removing the dust when it does collect, and building dust-tolerant equipment. And I know Honeybee Robotics is working on a lot of this, but just like in everyday lab safety, when we do work on the moon, the best idea is to mitigate the hazard before it even exists. Number one. This is where SPIDR comes in, the simulator for planetary interactions of dust and regolith. This is a discrete element modeling simulation that can be used to predict how wheels, excavator buckets, and more can be used safely to limit dust mitigation on the lunar surface. We hope to answer questions such as how does tool or wheel geometry affect dust mobilization? And how can we inform the design to limit this? Currently in this model, we're considering the lunar surface environment, including ambient electric fields. We're also looking at charges of the regolith grains themselves. Also included is grain size and bulk porosity. And right now, this talk, the main calibration I'm going to be discussing is cohesion and frictional properties of the simulated regolith. So different cohesive mechanisms in the regolith within DEMs are simplified to what they call a cohesive energy density parameter, or CED. Particle behavior is dependent on this and other things such as rolling friction, sliding friction, and more. There's published studies on how these calibrations work, and here we are just following these established methods. Here is our initial calibration experiment. On the left is the uncalibrated. This is just an initial model run, a proof of concept of how we will calibrate. The right side is a funnel slowly being lifted up and forming a pile of angle of repose and measuring the angle of repose using Exolith Lab Lunar Mare Simulant LMS1. This calibration will consist of doing an intelligent search through stochastic methods to find the optimal value of cohesive energy density, as well as other rolling friction and so on that give the best fit to the data. We're letting the data tell the story, not the model. So how do we build this simulation? We use LIGHTS. It's an open source discrete element modeling program to intake a CAD model of a simplified Apollo 16 LRV wheel and fender. But again, we can take in any design. If you have a CAD model of a tool or wheel you'd like to simulate on the surface, we can do that. This is just our proof of concept. So after we create the rover wheel and the model, we define our particles, their size, the distribution of sizes, their charge, cohesive properties, and so on. Then we run the simulation by inserting the particle into the inserting particles into the tray, lowering the wheel into the particles, and rotating and translating the wheel accordingly. As far as initial testing and kind of gut checking our results, we're looking at the LRV Grand Prix that they did during Apollo 16, where again, astronaut flooring it. we all like flooring it on Earth. We probably shouldn't just floor it around on the moon. Look at all that dust. That, again, presents hazards to human health and equipment. We want to mitigate this risk as much as we can through things such as a lunar speed limit, perhaps, for rovers. So we run our models, and there's 3 different test cases here. One with grains of 0.1 micron, the middle is 50 microns, and then the combined fractions on the right. The properties are the exact same here. The only change is the particle size. Running these simulations, lowering the wheel into the regolith, and we see dust being kicked up. In the combined one, the red dots are the 0.1 micron radius particles, and the white are the 50 micron radius. Highlighting a bit more detail, because sometimes those small dots can be a bit hard to see. We see the distributions of the particles separately actually matching pretty well to the combined fraction. This can be used, this modeling, this technology, can be used to study and inform designs and operations of things like the Lunar Terrain Vehicle and other rover designs. SPIDR will help us assess inputs as tool paths, forces for ConOps on the lunar surface that we can validate through models to help us design better equipment, optimize ConOps, and ultimately make operating on the lunar surface a more efficient process. Again, our test case is the LRV wheel that we're using here, but we can take in any tool, and that's the beauty of this. This is a material property calibration study. We're interested in the regolith properties. You don't put in the right properties, you don't get valid results. So again, regolith is everything. After we have those properties, we can do whatever tooling you want. So in summary, we have created a DEM simulation to analyze ConOps and tool paths, including rover wheel trafficability on the lunar surface. Preliminary results show that different particle sizes will be distributed unevenly through space in the dust cloud. And further development of this model is planned. And at Exolith Lab, we are in collaboration with the University of Notre Dame building a single wheel testing rig called Rider that one of our students is presenting at the poster tonight. So we'll be able to validate results from actual wheel testing with gravity offloading to our simulated models, a full validation and verification of these technologies. Here's the acknowledgements, and I'm probably running about up on the 2-minute mark. Does anyone have any questions?
We do have time for a quick question or two.
I'm just wondering, of course, the material properties play an important role. What is validation in your mind? Looks like it? You get the same size distribution? What is validation in
there's no looks like here. This is a quantitative model. We're going to be doing statistical estimates of grain size distributions throughout the dust cloud. For the initial calibration using angle of repose, we're going to be using numerical methods to estimate the average angle of repose, estimated through thousands of samples of model inputs, and doing statistics to find the best fit mean within whatever confidence interval you want, but 95% is the standard.
You showed the cloud in small and big and mixed.
Mm-hmm.
It doesn't look like the rooster tails. So what are, it's...
There are currently no statistics on that. This is an in-development program.
Okay.
I'd be happy to chat further, but we're just about to launch into calibration stuff, and the statistics comes out of the calibration. Right now, this is just a proof of concept to show that we can run the models, and then from there, we begin our stochastic-based calibration.